Welcome, Math 107 students, to the activities for Lesson 21 on polynomial functions and their graphs. So earlier in our demo, we introduced you to some new language. So this chart here is to help you with some of that new language and also to this new idea of the end behavior and how we actually write the end behavior of a function. So here's a polynomial. It's degree 3 because the highest power you see is a 3. The leading term is the term that has the highest degree in it, so that's 2x cubed. Your leading coefficient of your 2x cubed is the number that multiplies x cubed, which is 2. And our constant term is the constant that appears here, which is 4. If you don't see a constant, then you can write 0. This is an odd function, an odd degree, and we know odd degree, our end behaviors go in different directions. So since the leading coefficient is positive, that tells us as x moves to the right towards positive infinity, our graph continues to grow, our output values continue to grow without bound. They rise, rise, rise. And as we move to the left towards negative infinity, our graph falls and it moves towards negative infinity. All right, so let's fill in this table. I'm going to give you a minute to fill in as much of this as possible. And I'm going to take a break and fill it all in. I'll do one row with you, and then I'll give you some time to fill it in. So the next polynomial has a degree of 5, since that's the highest exponent you see. The leading term is this entire term right here, right in front of the addition sign. Remember, your terms are all the pieces on either side of addition and subtraction. That's what a term is. So the term is 3/2 x to the 5th. The leading coefficient is the value, the number that multiplies x to the 5th, so that's 3/2. And the constant term here would be a 0. Okay. Again, this function is going to have the same end behavior as the one above it, this polynomial, because they're both odd degrees and the coefficient, the leading coefficient, is positive. So you can fill this part of your table in exactly the same. Okay, the next function, we might as well just work these together. Most of the time, we suggest that you put this in what we call descending order. You don't have to, but if you put it in descending order with your highest power first and then your next power all the way down to your constant term, if you have one, then you can just proceed the way we've proceeded. The degree here is 7, but you could have picked that out without rearranging it. The leading term here is the entire thing, negative 3x to the 7th power, and your leading coefficient is negative 3, and our constant term is 1. So even though this is an odd degree polynomial, because the leading coefficient is negative, that tells us that as I move to positive infinity, as I move to the right towards positive infinity, my graph is falling, so I'm moving towards negative infinity. And we know that with odd degree functions, our arms, our ends rise and fall. If one rises, the other falls. They work in opposition. They don't work in the same way. So now as we move towards negative infinity, our function will be increasing without bound, and that will move to positive infinity. So now if you look at these last two functions, the biggest difference between these two functions and the functions above, see if you can figure out in your own mind what the biggest difference is. Okay, I hope that you said that these functions were all multiplication on the right-hand side. They were all in what we called factored form. So now to find the highest degree, you just don't pluck off the exponent for your leading term because there are no terms. This is not adding and subtracting. Now, some of you will probably only feel comfortable by multiplying this all out. This would give you x squared minus 4. And then that would give you negative x to the 4th plus 4x squared in order to answer these questions. But I want to show you a little shortcut or how you can determine the degree of a polynomial function even if it's factored. So what you do is you say, okay, there's a 2 here for an exponent. Well, even though the exponent isn't there on x plus the factor x plus 2 and the factor x minus 2, it's understood to be 1 for each of them. So if you were to multiply x squared times x, you'd get x cubed, and then x cubed times x, you'd get x to the 4th. So one way to determine the degree of a polynomial when it's entirely factored is to add up the exponents. That's the only time you would do it, is when it's in completely factored form. So the degree here is 2 plus 1 plus 1, which is 4. Okay. Now, if you're not feeling convinced yet or comfortable, you could multiply x plus 2 times x minus 2 and get x squared minus 4, and then multiply each of those terms by the opposite of x squared to see why it's a 4th degree. Okay, our leading term here is negative x to the 4th. Our leading coefficient is negative 1. This is an even degree, so in this, and the constant here is 0. So here either both of our long-term behaviors will be going in both directions, either stretching towards the sky, both rising or both falling. So since our leading coefficient here is negative, it's going to be drooping. Just think about your basic parabola. If the value of a, your leading coefficient, was negative, it would be a sad parabola opening downward. So both of these, as x goes to positive infinity and negative infinity, your function continues to fall, 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 fall. Okay, now the last one, if we use some of the ideas we just learned in the row above, this is completely factored. Yep. So to find the degree, I just add up my exponents. 2 plus 1 plus 2, another odd degree. Okay, so how do you determine what the leading term would be? Well, this number, this coefficient here, is always the same. Notice the negative 1 here was the same as the leading coefficient. So 1/9 is the leading coefficient, whether it's in factored form or we write this all out in polynomial form. Now, I don't know about you, but I don't want to square this, multiply all three of these things together just to determine what the leading coefficient is. And guess what? I don't have to, because all you have to think about is x to what power? Well, you know if you square this, you're going to get an x squared. When you square this, you'll have an x squared here. You'll get an x here, because this is just to the first power, and you'll get another x squared from this third factor. So you would get an x to the 5th. So your leading coefficient is 1/9 x to the 5th. And your constant term here will be 1. And I'll let you think about that for a little bit. And if you can't figure it out without multiplying it all out, send me an email. I'd be glad to talk about it with you. But I'll just give you a hint. Now remember, if you multiplied all of this out, you'd have a bunch of stuff here, and you're going to have some constant right here, plus or minus some constant. Don't forget that the 1/9 will be multiplying that constant. That might help you. Okay, it's odd, and the leading coefficient is positive, so this looks just like our first two. Okay, so let's take a look at some applications of the material that we've learned. And as we do sometimes, we are going to give you some more information that you should consider or take notes on in this activity. So here we have a polynomial function. It's a nice smooth curve. As we move to the right, our polynomial function is increasing without bound, and as we move to the left, it's falling or decreasing without bound. So what is the degree of this function? If you didn't have this equation right here for the function, you would know it was odd because your end behaviors are acting in opposition to each other. One, your right arm is up and your left arm is down. Okay, so, but since we have the actual function, we can see the degree is 3. How many zeros does f have? Remember, zeros are the values of x that make my function 0. We typically find these by looking for our x-intercepts. So as you can see here, you have a 0 at -2, a 0 at +1, and a 0 at 2. So when you answer a question like what the zeros are of a function, you don't put down the coordinates for the x-intercepts because these zeros are values of x that when you plug it into this particular function, for example, f of 1 is 1 cubed minus 1 squared minus 4 times 1 plus 4. That equals 1 minus 1 minus 4 plus 4. That gives you 0. So these are actual solutions to this equation. What values of x make my equation 0? Just like when you solved a quadratic equation that you set equal to 0, you were finding solutions. So if you wanted to, you could put these into a solution set just like this, or you could leave it like this. But what we don't want to see when we ask you for zeros of a function is we don't want to see parentheses -2 comma 0 parentheses. We don't want to see coordinates because in this case that could look like an interval, right? All the numbers between -2 and 0, and that's not what's going on here. So this is just the only change for it's kind of the same idea that you've been used to doing and calling x-intercepts. It's just the fact that we're solving an equation, so these are actual solutions. All right, how many relative maximums and relative minimums, also known as relative extrema, or turning points? Kind of turning points is kind of a nice friendly name, isn't it? Instead of all this relative max and min stuff, right? Hills and valleys. Turning points does f have? Well, f has a turning point right here because prior to this point, our function is increasing, isn't it? Function increasing. Then after this point, our function is decreasing. So that's what we call a turning point. And then down here, between 1 and say 1.5 here, our function was decreasing. And then just to the right of 1.5, our function decides to increase again. So we have 2 turning points, or 2 relative extrema. That's kind of a big word for that idea, right? So now we're trying to figure out, hey, is there a relationship between the degree of my function, the number of zeros, solutions to this equation I have, and the number of turning points? Well, guess what? There is. Okay, so notice I have this highlighted in big, bold, important. So you definitely want to highlight this in your packet. You want to probably write this into your notes. In general, if f is a polynomial function of degree n, so in this case it's degree 3, then the graph has at most n-1 relative extrema. In other words, we have at most 2 relative extrema. We can't have more than 2. We can't have 3 when we're a third degree. So what does at most mean? It means it can have 2. The question is, can it have 1 and can it have 0? So let's take a look at that for a minute. So any cubic functions will always have some form like you just saw, like that, Or they may be like this, okay? Or they could be some variation of the parent function, which is always increasing like this. Maybe you're just shifting this right or left or up or down. So notice this has two turning points. The first two that I showed you has two turning points. But guess what? This function, or if we make the coefficient negative and we do this, whoops, going through, that's supposed to go through the origin. Both of these have 0 turning points. So with regard to an odd degree of 3, a cubic, you can have 2 turning points or 0 turning points. So let's look at another function and figure out what's going on. Okay, so here's a function. I want to find the zeros and state whether each multiplicity is even or odd. And let's go a little bit further and see if we can actually guess the value, what the multiplicity is, the actual number of multiplicities, okay, based on the graph. So the first thing I notice is, look, my end behaviors are both rising. They're going together in the same direction. I know that when I add up all of my factors here, the exponents for all of my factors, I will get an even degree. So the first thing I know is that I have an even degree polynomial. The question is, could it be 2? Well, clearly that is not a parabola, right? Now, could it be 4, 6, 8, 10? Well, that's what we're about to decide. And we always want to just state the minimum degree it can be. We know it can't be a 2. Now the question is, could it be 4? Well, let's check out how many hills and valleys, turning points, relative maximum and minimums we have. 1, 2, 3, 4, 5. So we can't have more turning points than the degree. So it can't be 2 and it can't be 4. Those are both out of the contest for being the degree. So let's work through this problem. We know it's going to be an even number higher than 4. That's just the type of thing you can start to look forward to now as you work through your problem. You have that amount of information already in your toolkit. Okay, so the first 0 that I see as I move from left to right is I see a 0 at -3. And since at this 0, let's see if I can find my magic pen up here. There we go. If I just zero right in to that area and look at that behavior, the behavior of my function near my 0, I see that I bounce. I was a positive value of y, I went down to 0 at -3, and then I bounced right back up. That happens, and if you look at that, doesn't that look like a baby parabola right there? So that means I have a multiplicity that's even, and I'm going to say my multiplicity is 2 here. Now, maybe it's 4, maybe it's 6, but since it's not really flat there and it looks just like a parabola, I'm going to say 2. We always go for the smallest at this point. Okay, when we're trying to determine the minimum degree. Where's the next 0? I move along on my x-axis. Oop, here's another one at -1. So let's see what's going on at -1. Let's get out that magic pen and see what's going on. Blow that up. I wonder if I can make that bigger. Well, I can make the circle bigger, but I don't really want the circle to be bigger. So notice I'm going straight through that axis, right? I'm going, the sign of my function is positive when I'm to the left of -1. I'm above the axis, x-axis, and then I become negative. So this means I have an odd, when I change sign or I cross the x-axis, I have an odd multiplicity. And since there's no squiggling around that -1, it looks sort of like a straight line when I blow it up. I'm going to say the multiplicity is 1. So as I do this, let's go down and fill in a possible equation. So all of your polynomial equations, when you're looking at a graph like this, you'll start off in factored form. So this is the box for the leading coefficient. In each one of these spots right here, you're going to put your 0. And your exponent will be your multiplicity. So what have we gotten so far? We've gotten -3 as a 0. So that means that my factor would be x take away a -3. So x take away a -3 will become x plus 3. And we decided it was an even multiplicity, and 2 would be the exponent for that factor. The next factor will be x take away a -1. So x take away a -1 will change this to x plus 1, and our multiplicity is 1, since we go straight through like a line. A linear function has degree 1. All right, now we're moving along. We don't confuse your y-intercept with a 0. A 0 is your output of your function when your function is 0, not when x is 0. Sometimes students try to include the y-intercept here. So our next 0 is 1. And if we blew 1 up with our magic pen, let's take a look. Our magic pen, and see what's going on right near that 0 of 1. We can see we're bouncing again. We were negative to the left of 1, and we're still negative after we go to the right of 1. So we're bouncing, we're not changing sign. That means we're even. And I'm going to guess that I have a multiplicity of 2. So x is 1. That means my factor looks like x take away 1. Because when I write my factors, they all start off with subtraction. They all start with subtraction, and if my 0 is a negative number, then it changes to addition. And my multiplicity is 2. Then finally, let's see, maybe you could take a guess as to what would be the last factor here in the multiplicity by looking at the graph. I'll give you a moment, see if you can fill that in. Okay, so we see that our final 0 is 3. It changes sign, it crosses the x-axis, no squiggling or moving around there. So it goes straight through, it's an odd multiplicity, and I'm going to assign 1 to the multiplicity. So it's x take away 3, and 1 is the multiplicity. Woo, that was a lot of work, wasn't it? Well, it actually goes pretty quickly once you get the idea down. So this is what we have right now. We have f of x equals a, our leading coefficient is this box. We haven't figured that out yet. Times x plus 3 squared times x plus 1 to the first times x minus 1 squared times x minus 3 to the first power. So now this is just like all the problems you used to work in intermediate algebra, where you had to find the value for b when you were looking at y equals mx plus b. And even once you knew the slope, say the slope was 2, and you still had to find b, you picked any point that you knew existed on that line, and you plugged the value in for x, and you plugged the value in for y, and you were able to solve for b. The same is true here. I have one last thing to solve for, and that's a. So I need a little birdie to come along and tell me a point, not these zeros. They're not going to help me, because if I put in any of these values here, -3, -1, 1, or 3 in here, I'm just going to get 0. That's not going to help me determine what a is. So you have to pick one other point that you know is on this polynomial function. And guess what? You've got a beautiful point right here. And the reason I say it's beautiful is because x being 0 is going to make this happen really quickly in terms of doing the arithmetic. So what does this say? It says when I plug 0 in for my x, my y value is -3. So I'm going to plug 0 in for all my x's, and I'm going to leave a -3 here as my output. So when I put 0 in here, you can see now how quickly this arithmetic will happen with 0. So let's make this into an equivalent equation. We have -3 equals a times 9 times 1 times 1 times -3. So that's -3 equals -27 times a. So a is 1/9. Woohoo! So we figured out the entire graph of this polynomial, right? Isn't that cool? You know, did you think maybe a couple of weeks ago you could have figured out the equation for this polynomial? There you did it. It's right here. So you could erase that 1/9 right here in front, and you've got the whole enchilada. There you go. All right. So we actually had a polynomial in that table that we looked at just a minute ago. Oh, it's almost the same exact one. Not quite. This was an odd one, but we had 1/9 there for the leading coefficient as well. Okay, so let's see what else we have. Let's just finish that last question. So the smallest or lowest possible degree for this polynomial would be to add up all of your multiplicities here. The smallest degree would be 2 plus 1 plus 2 plus 1, which is 6. We knew it couldn't be 4, we knew it couldn't be 2, so we'll say 6 is the lowest possible degree. All right, now we have some fun with graphing these polynomials from given certain information. So let's take a look at this number 4. Number 4 says to use the 5-step strategy. That's just something that they've mentioned in the textbook to graph x cubed minus x squared minus 6x. I only have 6 minutes left before this class comes in, so I'm going to go through this rather quickly. So since this is an odd degree, I know this will be my end behavior. So we have negative and positive infinity and negative infinity here. We find the x-intercepts of the zeros of the function by setting f of x equal to 0 and solving this equation, which is a polynomial equation. So the GCF is my best friend. Okay, so when I factor this, this is what I get. And I see that I have 3 solutions or 3 zeros. I have x equals 0, 3, and -2. So I have -2, 0, and 3 as my zeros. And on my graph, they're x-intercepts. Find the y-intercept by computing f of 0. When I put 0 in here, since I have no constant term, 0, 0 will also be my y-intercept. Do I have even symmetry, odd symmetry, or none? Well, since I have a mixture here of odd and even exponents, this will be none, but you should check out seeing if either of these two statements, or to show that these two statements are not true. This is the check for even symmetry, and this is the check for odd, and neither of those two statements will be true. Find the maximum number of extrema. Well, since my degree is 3, n equals 3, the maximum number of extrema is 1 less than that, which is 2. So a possible graph here would be to start down here, head towards your first 0. You know that you're going to cross over. Why? Because all your multiplicities are 1 at those zeros. So you will be crossing the axis at each of these. So you go up, you come back down, you go back, oops, you come back down because you don't bounce, and then you come back up. Okay. The next one, I've got students waiting out there, so I'll keep trying to finish this up for you. Find the graph for this. Now we're all in factored form. We know if we add up those multiplicities, we're even. The leading coefficient A, the leading coefficient is -1. So that means my graph will be falling, 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 both in the same direction. I don't have to factor this. It's already factored for me, which is kind of nice. This was one from our earlier table, if you remember. And so here we have 3 factors that we set equal to 0. So here are our 3 zeros, -2, 0, and 2. The y-intercept, when I plug 0 in here, let's see what I get. 0 squared, the opposite of 0 squared, times 0 plus 2. So this is f of 0 times 0 minus 2. That gives me 0 times 2 times -2. Guess what? 0 times anything is 0. So that means the 0, 0, our origin is acting as both the x and y-intercept. The symmetry here, again, I'll let you determine that. Find the maximum number of extrema. Our degree is 4. So we have 4, take away 1, we have 3 extrema. So what do I know about each of these? I know that at -2 and 2, my graph is going to cross through the x-axis, and at 0, I'm bouncing because I have an even multiplicity. So, okay, I'm going to come up here. I'm going to cross over. I know I got a bounce right here, so I just go up some amount of the way. I don't really care how high it is here. And then I come back up, and then I shoot down. And you should find that you have even symmetry here. So the right side and left side look like carbon copies of each other, even symmetry. Oops, I spelled symmetry wrong. All right, let's finish off this very last one. Draw 3 possible sketches. Well, you actually have some examples in your answer key, but again, degree 3 with 3 real zeros and a positive coefficient. All you need to know is that your ends are going to look like that. You pick any 3 places on your x-axis to put your zeros. It doesn't really matter where it is or where they are. So I'm just going to go like this. I'm going to come down like this, and I'm going to go like that. So that's a possibility. And now a degree 4, but the leading coefficient is negative. I know that my graph falls as I move to the right and the left. And I have 2 real zeros. Ooh, with degree 4, that means that I have some zeros that look like this. Here's 1 0, it will be squared, and here's the other 0, and it will be squared. And all I know is that my leading coefficient is negative. So since I have only 2 unique zeros and my degree is 4, then they both must have a multiplicity of 2, so they're going to be bouncing. So I'm going to go out to -4, and I'm going to go to +4, and I'm going to draw a graph. I'm going to come down here and come back up here, and there I go. Okay, so those, again, are just quick sketches of the possibilities. Okay, if you have any questions, please call me. Thank you. Not call me, sorry. Email me. What are you doing?